Hi, in today's video we're going to talk about how you can do an anti-Markovnikov addition onto an alkene. So you use borane. This is a new reagent that we're going to talk about today. So far we've been talking about Markovnikov additions, so the addition that will occur at the site of the more stable carbocation. So if you add acid to an alkene in the presence of water, that water will add to the more stable carbocation. But what if we want instead this secondary alcohol instead of the tertiary alcohol, where this would be the less stable carbocation location? So this is the anti-Markovnikov location. Well, as is often the case with organic chemistry, there is a reagent for that. So the reagent that we use is actually a series of two reactions. The first is to treat the alkene with borane, BH3. And then in a second step, or actually in the same flask, but you just add more stuff to it, you add hydrogen peroxide in the presence of sodium hydroxide. And this now gives you the alcohol. So the actual oxygen that is on your final molecule comes from the hydrogen peroxide oxygen. And we'll look at a mechanism of that later. So as is often the case with alkenes, we like to look at cyclic alkenes to better understand what's happening. One thing to notice is that the hydrogen of borane is the hydrogen bond that's been made to your molecule. So there is evidence of the fact that you started with borane. You don't see a boron on the final molecule though. So if we start with a cyclic alkene and we treat this with borane and hydrogen peroxide, what you'll observe is this as your final product, but it really doesn't tell you how you got there. Here's what we're going to look at. The hydrogen atom that was added to the molecule and the resulting alcohol that is formed are syn to each other. They're on the same face of the molecule. And that has to do with the mechanism of how this is done. And again, the location of the alcohol is not at the site where there would be a more stable carbocation, which would have been here, the tertiary carbocation. Instead, it's at the site of where a secondary carbocation would have formed had you undergone a reaction that had a carbocation forming. And so that's why we call this anti-Markovnikov. So let's look at the mechanism. So this first portion of the mechanism is that you have the alkene and you have borane, and the bonds are all aligned kind of as drawn here. So it's important to remember that boron has this empty p orbital, and the electrons from the double bond will interact with that empty p orbital. At the same time, so in a concerted fashion, a single transition state, the boron-hydrogen bond is breaking, and you're forming a carbon-hydrogen bond at the same time. So the transition state looks something like this, where you're breaking this double bond, forming a bond between carbon and boron, breaking the boron-hydrogen bond, and forming a carbon-hydrogen bond. So there are two ways of thinking about why the regioselectivity, or why the boron winds up on this carbon as opposed to this carbon. So one piece of the logic is that you are forming a partial positive charge on the more substituted carbon. So that's kind of like a Markovnikov argument. And that is, and you're forming a partial negative charge on this boron atom. The other thing to think about is that boron takes up three-dimensional space, and the more hindered location is this site where you have the extra methyl group. And so the hydrogen will go to the least hindered location. So again, because boron, even though it's not very large, is significantly larger than hydrogen. So after all the bonds are formed, you end up with this borane and hydrogen atom syn to each other. So this purple bond and this red bond are on the same side of the molecule. If you were to draw the arrow pushing mechanism without drawing the transition state, you'd simply draw these arrows. You wouldn't have to draw in this p orbital. You just simply draw in these arrows and this line going down to this product at the right. So now another thing to look at is that there are ways of making this even more of the dominant product. So let's say there is a subtle difference in size between the two sides of the alkene. In this case, you can use a reagent called 9-BBN, and there are others that do this as well. But in this case, 9-BBN, you can effectively think about it as bulking up one side of this borane with large alkyl groups, and this will be even a bigger steric encumbrance on this transition state, so it will make it even more favorable to have this big steric wall further away from this methyl group. All right, so now let's look at the next set of reagents. So we add hydrogen peroxide and sodium hydroxide. The interesting thing about this reaction is that this provides retention of this stereocenter. So the boron carbon bond and the oxygen carbon bond are both facing the same way, so you wind up with a syn alcohol product. And I'll show you the retention or the mechanism behind this retention, and this mechanism is really a bonus. You will not be asked for this, and this is not presented in many of the books, but this is what's happening, this is why it's happening. It's actually a rearrangement. So when you add hydrogen peroxide and base together, the base deprotonates hydrogen peroxide. And so now you have electrons, a negative charge, and a boron with an empty p orbital. So you're going to form an oxygen-boron bond, and that's highlighted in purple here. So now you have a boron with a negative charge, a formal negative charge, and you have this arrangement of electrons. What happens now is a rearrangement reaction where the electrons in the carbon-boron bond go to form a bond to the oxygen atom, and now you have hydroxide as a leaving group. One of the reasons this occurs is that this oxygen-oxygen bond, highlighted in red here, is really weak. So often when you bind two heteroatoms, like oxygen to oxygen, or you've seen this in the case of halogens, bromine to bromine, chlorine to chlorine, that bond between the two electronegative atoms is often quite weak. And so when you do this, you've now moved the bonds over, and so this oxygen is now bound to carbon. It is still bound to boron via this bond highlighted in purple. So the hydroxide can now interact with boron's empty p orbital again and displace the boron from the oxygen. So you break that oxygen-boron bond, giving you this deprotonated alcohol product. So at this stage, we can now add a workup step. So we would add a little bit of mild acid to the solution, and that mild acid will protonate the alkoxide and give you your resulting product, that is the secondary alcohol. And again, I'll highlight with the colors, the oxygen atom that acted as the first nucleophile to the boron is the one that winds up on the resulting molecule. Thank you for your time, and I look forward to answering your questions in class.